Good day. Welcome to your mathematics lesson for today. Now, in our previous live session, we talked about some couple of interesting concepts. We talked about the fact that we could represent cyclical patterns in real life as well through a concept we call modular arithmetic. We looked at the fact that modular arithmetic represents equivalent values for each numbers. For instance, the equivalent values in modulo 4 is simply the values from 0, 1, 2, and 3. So any other number that you represent in modulo 4 will simply take this equivalent form. We call this equivalent form a set of equivalent classes for the modulo value. For instance, if we were to pick 15 mod 4, then this would be equivalent to 3. We talked about the fact that we could calculate that equivalent value using the concept of long division, where the modulo value is outside and then the number is inside. Then you divide normally, the quotient comes on top, and then the remainder is your equivalent value. We also talked about the various ways in which modular arithmetic can help us in normal day life. For instance, in our clocks, in our wall clocks, and in our digital clocks as well. We talk about the fact that the analog clock is in a modulo value of 12. As the cycle starts from 12 a.m. back to 12 p.m., it repeats that cycle from 12 p.m. back to 12 a.m. You'll find out that, of course, even though we have 12 inside, and we have said that the modulo values in that, or the equivalent classes in that modulo value, cannot have the same results as the modulo in this form. We simply know that even if we say 12, in modulo 12, we are simply referring to 0, right? However, we are not putting in 0 simply because putting in 0 would become much more complicated as far as telling the time is concerned. It's going to be very, very complicated talking about 0 a.m. or 0 p.m. or 0:30 a.m., stuffs like that. So it's easier for us to just retain 12 value. But remember that 12 is simply an equivalent result for 0, just as 0 here in mod 4 is the equivalent result for 4. So if we say 4 mod 4, this is equivalent to 0, right? We also talked about the use of modular arithmetic in the days of the week. If you start from Sunday as the first day of the week, you go to Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. By the time you get to Saturday, you are reversing the process back to Sunday. It's a cyclical pattern, which means that all the numbers you can have fall within that pattern. So even if you say you are in the 28th day of the month, that 28th day will fall into one of those days of the week. In fact, for the months of a year, they also follow a modulo class of 12, because once you start from January to December, the pattern repeats back to January, right? And so on and so forth. These are interesting concepts we talked about in modular arithmetic. We also talked about the fact that you can carry out operations between modulo classes. For instance, you could find the value of 15 mod 7 plus 13 mod 4. First is getting the equivalence values. You could find this again via long division, 7, 15, 2 here, you have 14, and then you have the value here to be 1, and then do the same long division on this side, and then you'd have this as well to be 1, which means that 15 mod 7 plus 13 mod 4 will be equivalent to 1 plus 1, which is equal to 2. We talked about how we could carry out operations on modular arithmetic like so. When we finished our discussion, or the moment we finished our discussions into modular arithmetic, we looked at something even more interesting, and that's the concept of sequences and series. And in fact, we started one of the basic, or one of the most important sequences in the world, and that is the arithmetic progression. We talked about the arithmetic progression as a sequence formed when a common difference is added to the first term to get the second term. The common difference is added to the second term to get the third term. Common difference is added to the third term to get the fourth term, and so on and so forth. We also generated the standard AP sequence, which we term as the first term, followed by the second term, which is the addition of the common difference to the first term, followed by the third term, followed by the fourth term, and so on and so forth. We now generated that from this arithmetic progression, we can get a set of series such that we are adding the terms of the arithmetic progression up to a particular number of terms. So we say that the series for the AP can be simply written as the first term plus the second term plus the third term plus the fourth term and so on and so forth, right? So we are continually adding the number of terms needed to find our sum. We also generated some formulas. If you have the sequence of arithmetic progressions, you can find the nth term of that arithmetic progression as a plus n minus 1 d. And then if you have the sum of the arithmetic progression, you can find the sum of the first n term of that arithmetic progression as n over 2 into 2a plus n minus 1d, or by a shorter formula, n over 2 into a plus ln, right? This is how we define the sum. Of course, we have two formulas for the sum, because if in the first case you do not know what the nth term is, let's say you're looking for the sum of the first 15th term, however, you had the number of terms, which is 15, you have the first term, and you had the common difference, you can always use this first formula. If in this case you had the first term and the nth term, which is 15th term in this case, we are talking about the sum of the first 15 terms, for example, then you can simply use this formula. So the choice of the formula depends on the parameters you have to solve. Now, let's go into something even more interesting. Today, we'll be talking about the concept of geometric progression. This is, again, another kind of sequence. Great. Now, let's continue on our part for today's live session. We are going to begin with geometric progression. Now, for geometric progression, again, it is still a kind or a derived form of sequences. However, unlike the AP part, where it is formed from the addition of the common difference with a term to get the next term, for this GP, it is formed from the multiplication of what we call the common ratio with the first term to get the second term, multiplication with the second term to get the third term, and so on and so forth. Let's give a scenario. So we are saying that the GP is formed. First, you have to have a first term. Let's call it A still, and then let's have a common ratio now in this case. Now, to form the geometric progression, we are simply going to pick the first term and then multiply it with the common ratio to get the second term, multiply the common ratio with the second term to get the third term, which is AR squared, multiply the common ratio with the third term to get the fourth term, which is AR cubed, and so on and so forth. This is how to generate the geometric progression. We can also talk about this nth term of this geometric progression, just as we have the nth term for our arithmetic progression. Now, for the geometric progression, the nth term ln is given as AR raised by n minus 1. And we can use this to find any term value we are necessitated to find. Recall that if we were to put, let's say, n to be equal to 3 here, and you put it into this formula, you are going to get this value of the third term. If you put n equal to 4, you are going to get this value of the fourth term, and so on and so forth. This is how we can use this formula to generate the nth term, whether it's the 50th term or the 150th term or the 250th term. Either one is fine. Now we have generated the sequence of geometric progression. We can also generate the series of that geometric progression as well. For the series, all we are simply doing is what? Adding the terms up to the number of terms required. So we can write the series of the geometric progression as A plus the second term plus the third term plus the fourth term plus up to the point we are getting to, right? Now, what makes geometric progression very, very interesting and intriguing is the fact that because of the peculiarity of the common ratio, which is how it is formed, in fact, you can get the common ratio as the division, because we are talking about ratio, which is obviously going to be division. It is simply the division of the second term by the first term, and has to be equal to the division of the third term by the second term, and has to be equal to the division of the fourth term by the third term, and so on and so forth. Right? You will see that if you simplify all of this, you are going to get R as your result. So because of the peculiarity of the common ratio, coming from the fact that it's a division process in order to get it, it means that we can consider the various forms the common ratio can exist in order to find the sum of this geometric series. Now, there are two major forms in which the common ratio can have, and then one derived form which comes as a byproduct of those major forms. The first major form is if the common ratio happens to be greater than 1, what happens? If the common ratio is happening to be greater than 1, the first principle the sum of a GP or the geometric series follows is that it wants the denominator of its formula to always be positive. It wants the denominator to always be positive, which means that we can derive the denominator of that sum of n terms of the GP if we can correctly consider what the common ratio is. If the common ratio is greater than 1, this suffices by inequality that we are saying that r minus 1 is greater than 0. All you just have to do is subtract 1 from both sides here. So if r minus 1 is greater than 0, it means that r minus 1 is positive. R minus 1 is what will exist as our denominator. Are we together? In our numerator, we are going to have the first term. Nothing is going to happen without the first term. And then in our brackets, we are going to raise each individual member of this denominator to the power of n. So r, we will raise it to n, minus, we are going to retain the sign in the denominator, and then 1 is raising to n, and 1 raised to power n will still give us 1. Are we together? This is how we can easily generate the sum of n terms for the geometric series when the common ratio is greater than 1. Recall, all we need to ensure is that the denominator is positive, and we can get that denominator from that value of the common ratio. Similarly, for our second case, if the common ratio is less than 1, what happens? Then remember, we still need the denominator to always be positive. So it means that we have to ensure a positive inequality here. The only way to do it is to subtract r from both sides, and we'll have that r minus 1 or 1 minus r is greater than 0. Subtracting r from both sides gives us that 1 minus r is greater than 0, which follows that the sum of n terms of the geometric series will simply first and foremost have a denominator of 1 minus r, and then the numerator would have the first term and a mirror expression of that denominator. So 1 raised by n gives us 1. The minus remains, r will be raised to the power of n. Simple and short. These are the two major formulas for some of the first n terms of a geometric series. Now, we have generated this term. We are also now going to look at the derivative form of the sum that can be gotten from one of these formulas. What happens when we want to continue the sum of the GP infinitely? That is, we don't want to stop at the first n terms. We want to continue toward infinite amount of terms, which means we want to take when n tends to infinity, or when n becomes very, very large. How then can we do it? Now, we will consider both cases and see if it is possible for us to calculate the sum to infinity directly from these two forms. Look at it. So let's have a check now. Let's check first and foremost if r is greater than 1. If r is greater than 1, we are talking about values like r equal to 1.5, like r equal to 5, like r equal to 5,000, like r equal to 1 million, for r equal to 10, values greater than 1. Now we want to consider when n becomes very, very large. We are going to be using our calculator to help us wrap our heads around this concept. If r is less than 1, if r is greater than 1, then it means that we are using the sum of n, which is a into r raised by n minus 1 divided by r minus 1. Right? That is not changing. Now we need it when n tends to infinity. So when n tends to infinity, we have s infinity. Let's look at what we'll have if it is going to be positive. A has no problem, it's the first term, it remains. R greater than 1 in the denominator has no problem. It will still be positive. However, what happens when you take R raised to the power of n? Let's now imagine this. Assume R is equal to 5, for instance. And then assume your n to be very large because it's tending to infinity. Assume your n to be 5 million. What would you have? You can attempt to press this on your calculator to just have a preview of what you'll be having. So let's have 5 raised to the power of 5 million. It gives you a math error. Why do you have a math error? Because 5 raised to the power of 5 million is a number that will be increasingly large, so large that even the calculator cannot give you an estimate. You can try with 5 raised to the power of 1 million. Let's see what happens. You still have a math error, which means that it is still incredibly large, so large that the calculator can still not give an estimate. If that is the case, it means that if you calculate the sum to infinity when the common ratio is a value greater than 1, which means it's a very positive number, and then the number of terms are increasingly large, then you would not be able to find the sum to infinity because it will also be very, very large. So large that even with an advanced calculator, you are not able to accurately quantify it. So it means that we cannot find the sum to infinity when R is just strictly greater than 1. If R is less than 1, let's see what happens. If R is less than 1 and then the number of terms still becomes increasingly large, we have a lot of values we can consider. We can consider values like -5, -3, -10, -5 million. Let's see what happens if you consider those values. Because R is less than 1, it means we are using the second formula. So you have that Sn is equal to A into 1 minus R raised by n divided by 1 minus R. Again, we don't have a problem with A. That's still a fixed value. Again, we don't have a problem with the denominator. That will still give us something reasonable. However, let's look at the numerator yet again. Let's consider what happens if we take -3 and raise it to the power of 1 million. You can have your calculator aid you again. -3 raised to the power of 1 million. Again, math error. Because that number is still incredibly large, whether positive or negative, because you know that if you raise a negative number to a positive power, you're going to have a positive result. For instance, -5 raised to the power 2 will give you +25. However, the number itself continually grows. For instance, -1 raised to the power 1 is -5, small, right? -5 raised to the power 2 is +25, the number has increased. -5 raised to the power 3 is -125. It's negative, but the 125 itself is an increment. -5 raised to the power 4 gives you +625. The number itself has continually grown, which means that if you take a negative number raised to a power that is very, very large, you are going to have a value that cannot be quantifiable even with the use of your calculator. So we can't find the sum to infinity when we just put the common ratio to be less than 1. Where then can we find the sum to infinity? We can find the sum to infinity within a small space of common ratio. We can find the sum to infinity if, and this is our derived value, if the absolute value of R is less than 1. And then when you say the absolute value of R is less than 1, you are talking about the fact that -1 is less than R less than 1. These are the range of values that you would have, such that if you put them into the absolute value, you would have a value that is strictly less than 1. For instance, -9/10. That's like say -0.9. If you put in absolute value, you still have 0.9, which is still less than 1. If you have 3/4, you have 0.5 or 0.75. Put that in absolute value, you still have a number less than 1. Values within this range will suffice in order for us to find the sum to infinity. Let's see why. If we have absolute value of R less than 1, first and foremost, it means that R is less than 1, right? So it means you are using this formula. So you are saying that Sn is equal to A into 1 minus R raised by n divided by 1 minus R, abi? Now remember that n is becoming very, very large. So n is tending to infinity. This means that we are asking for S infinity. Now let's consider what happens when we consider S infinity within this numerator. Now let's pick a value, any value. Let's pick minus 0.5 for instance. Remember that minus 0.5 will fall within this boundary, and then if you take the absolute value, 0.5 will still be less than 1. So let's do minus 0.5 raised to the power of 1 million. We have 0. You can try with something large to assuage our fears. We still have 0. Let's try with another number. Let's try with 0.3 and see what we have, or 0.15 raised to the power of 5 million. We have 0, which means that once the common ratio is between the values of minus 1 and 1, then if you raise it to any large number, regardless of how large the number is, all right, so if your common ratio is within the values of minus 1 and 1, and then you pick those values even when the power is becoming very, very large, that means the number of terms is becoming very, very large, you will still have that r raised to power n will tend to 0, right? Just as we check 0.15 raised to power 5 million, we had a 0 value. If you check minus 0.5 raised to power 1 million, we had 0 value, and so on and so forth. What does this mean? It means that if we were to find the sum to infinity within that value, we would have a into 1 minus 0 divided by 1 minus r, which will give us a divided by 1 minus r. So what does this mean? It means that to find the sum to infinity, of a geometric series, two conditions must be satisfied. Number one, the absolute value of that radius must be less than 1. The absolute value of that radius must be less than 1. If you can ascertain that, you are good to go. So in fact, this is the major condition you need to find. Or if you feel like this is a lot of problem for you, the next thing is if you feel like finding absolute value is complicated for you, just check if the value of r is within this range of minus 5 less than r less than 1. So it's either you check that the absolute value of r is less than 1, or you check that r is within the range of minus 1 and 1. Either one you check, if r satisfies those conditions, then you can find the sum to infinity of that geometric series. Now that we have picked a lot of formulas, we have this formula now, and we have this formula now, and then we have, so let me just write this then, S infinity is equal to a divided by 1 minus r. So we have this formula now. Now that we have these three formulas, let's now put these formulas to good use with examples, and we see different ways in which we can construct questions using these formulas. Let's get to it. At this point, let's now look at examples as to how we can calculate better using the formulas we have gotten from geometric progression. Let's take some examples. We have that first, the second term of a geometric series is 4, while the fourth term is 16. We have to find the sum of the first 5 terms, and we have to find the 15th term. Yes, so this is what we have as our question. The second term of a geometric series is 4, while the fourth term is 16. You have to find the sum